Hello, I am Professor S. Shankaran in the Department of Metallurgical and Materials Engineering.
Now we will move on to another basic mechanical testing called impact testing. Very important in industrial setup and very old uh, testing methodology, especially after the grand failures of Liberty ships and other catastrophic failures, which I mentioned in the beginning of the course. This test becomes quite popular to assess the ability of the material to undergo brittle fracture and so on. So basically, it is a fracture test. We are yet to get into that subject, but then we are looking at the mechanical testing. So I just want to complete this before we go to the other topics. So what is this impact testing? So this is the setup where you have this, hammer. The sample is kept in the anvil here fixed, and then hammer which and what is the sample dimension? This is a sample dimension. This particular experiment or test is called popularly known as Charpy impact test, and this is a Charpy specimen, and this is a geometry. It's kind of a 3-point loading setup. The sample dimension is typically 10 by 10 mm square, and with the notch in the center is about 45 degree. The root radius is about 0.25 mm. So which can be characterized or checked, cross-checked with the shadow camera and so on. So this sample is kept in this anvil, and then the hammer is going to bang this sample with the impact velocity approximately 5 meters per second. And then you can always calculate the initial height and final height and so on to arrive at this numbers. And what is that you get? So you just look at the result. What you get out of this test is impact energy versus temperature. So at various temperatures, these experiments are carried out, and then the plot will look like this for an FCC metals like copper and nickel. And for the high strength materials, especially sigma y is greater than E by 150. So the impact energy is going to vary with the temperatures like this. And for an FCC metals and, for example, polymer, which is typically polymers and iron, they're all going to show very different behavior. It's an S curve, right? As compared to other materials, they are going to exhibit this kind of impact energy as a function of temperature. And what is interesting to note here is the materials like VCC metals and polymers. They show something called ductile to brittle transition temperature. So this is very important. It's a characteristic of these materials, and then we will see how we are going to understand this, right? So we have the background for this, and this particular temperature is called ductile to brittle transition temperature, DBTT, popularly called as characterized as a DBTT. And what happens is the material will behave from up to this. At this temperature, it shows the transition from brittle to ductile to brittle transition temperature. That's called okay. So as the temperature is getting lowered, so it becomes brittle. So that is quite important test. So why these materials behave like this, and why some materials behave like this? So we need to understand this. Typically, impact loading is in the order of 10 to the power 3 per second. So we have seen these numbers in previously the one table I have shown all the various rate of loading, right, from the tensile to impact to very high strain rate test and all. So this is in the order of 10 to 3 per second. This is also come under the category of severe testing, and this kind of test makes material more brittle and decreases the toughness. Of course, with the increasing temperature, the percentage elongation increases, the energy absorption also will increase, and of course the Kc, that is the stress intensity factor, which you will see later, is also going to improve. Okay, what are the important points to note? The impact testing came because of the brittle fracture problem, like I just mentioned, right? Three basic factors contribute to brittle cleavage type of fracture. What are those? They are a triaxial state of stress, a low temperature, and a high strain rate, rapid rate of loading. All three of these factors do not have to be present at the same time to produce a brittle fracture. So even any one of these factors will cause the brittle fracture. A triaxial state of stress, you know what is it. Now you have sufficient background to understand this. Low temperature, that is what just we have seen, we have said in the previous slide, that then we will see why it is so in a minute. And high strain rate also makes the material brittle. A triaxial state of stress such as exists at a notch, because please remember we are making a notch in the Charpy test specimen, and the low temperature are responsible for the most service failure of the brittle type. So in general, a notch, that's why we simulate this notch in this test. So notch is a stress concentrator, right? So similarly, the low temperature, these combinations, or it could be either individual or a combination, is responsible for the most of the failures. However, since these effects are accentuated at high rate of loading, many types of impact tests have been used to determine the susceptibility of materials to brittle behavior. So this is a kind of an acid test to check whether the material is going to behave or it is going to failure by a brittle fracture. Okay. Because the root of the notches in a Charpy specimen is not as sharp as it used to be in the fracture mechanics tests, there has been a trend toward using the standard Charpy specimens, which are pre-cracked by introduction of a fatigue crack at the tip of the V notch. See, the 0.25 mm root radius is a standard Charpy impact test, which is normally practiced in most of the industry and R&D sector. But what happens is, and people believe that this 0.25 root radius is not a true fracture. I mean, the root radius is not sharp enough to assess the fracture toughness of the material. So how are we talking about fracture toughness here? We'll see now. These pre-cracked specimens have been used in the instrumented Charpy test to measure dynamic fracture toughness values, which is K1D. So instead of making 0.25 as a root radius, if you make a very sharp crack using fatigue loading, and then again, break this specimen under this test condition, you will generate a data and then determine the parameter called dynamic fracture toughness. It's very useful information. Okay, so that is why the pre-cracked specimens are being used. Now let us look at little more fundamental aspects. Why this material behave very differently? Different material behave differently. Common BCC metals become brittle at low temperatures or extremely high rates of strain. Many FCC metals, on the other hand, remain ductile even at very low temperatures. This particular aspect we have repeatedly seen in the previous lectures, right? We have seen there are two occasions we have seen. What is that? In one occasion, we said that the yield strength of BCC material is temperature dependent, right? Temperature dependency of the yield strength of BCC metal. That also, and that is one end. The other end is we looked at Pearl's Nabarro force in the very beginning, right? There also we talked about the stress required to move a dislocation in an FCC lattice and a BCC lattice, right? These are the two aspects we have to recall, and the temperature dependency of yield stress in a BCC metal. That also will the same. They are all will account for this behavior. Okay, that means these are the properties which are responsible for this kind of ductile to brittle transition temperature, because the BCC is the Pearl's Nabarro force is very high for a lattice like a BCC, right, as compared to FCC. Okay, so this is one of the primary reasons. When the slip systems on the basal plane are the only ones operating, polycrystalline HCP metals are brittle. So this is also known to us. When we say brittle behavior, suddenly we can also connect them to materials which has got a very restrictive slip systems, or restrictive number of slip systems rather. Okay, that is HCP. As there are not enough slip system to maintain the grain boundary integrity. This aspect also we understand it very clearly. Okay, how the limited number of slip system will have a problem with grain boundary integrity and so on. We have looked at a slip and the deformation mechanisms elaborately. You have a sufficient background to connect all this terminology. The conditions under which a material behaves in a brittle fashion, depending upon several factors. BCC metal generally require a high stress to move a dislocation, and this stress increases rapidly with the decrease in temperature. The stress required to propagate a crack, on the other hand, is not a strong function of temperature. So at some temperature called ductile brittle transition temperature, the stress to propagate a crack, that is sigma F, is equal to the stress to move the dislocation, that is sigma Y. So it's a very straightforward analogy, right? Straightforward aspect, how to understand this. At temperature higher than the transition temperature, that is sigma Y is less than sigma F, and the material first yields plastically. At temperatures lower than the transition temperature, the material is brittle. Here, the actual brittle fracture stress may be controlled by the yield stress, as some microscopic yielding may be necessary to nucleate a crack. So at all temperatures below the transition temperatures, when sigma Y is equal to sigma F, as soon as the applied stress reaches sigma Y, the crack is nucleated at the intersection of slip planes and propagates rapidly. So this way of understanding is also helps. Okay, when why this material behave like this. And then what is the significance of transition temperature curve? The chief engineering use of the Charpy test is in selecting the materials which are resistant to brittle fracture by means of transition temperature curves. That's the primary use. The design philosophy is to select a material which has sufficient notch toughness when subjected to a severe service condition, so that the load carrying ability of the structural member can be calculated by standard strength of materials method, without considering the fracture properties of the material or the stress concentration of cracks or flaws. So what does it say? See, it gives a rough idea before getting into very detailed strength of materials analysis or fracture toughness estimation, which we are going to see very soon. So this is a simple test, but gives a lot of fracture related problem, fracture mechanics solution. It gives a very rough estimate of fracture mechanics solution. High temperature materials, which is sigma naught is greater than E by 150, have Such low notch toughness that brittle fracture can occur at nominal stresses in the elastic range at all temperatures and strain rates when flaws are present. High strength steel, aluminium, and titanium alloys fall into this category. Okay. At low temperature, fracture occurs by brittle cleavage, while at high temperatures, fracture occurs at low energy rupture. It is under these conditions that fracture mechanics analysis is useful and appropriate. Okay, I will just not elaborate here. We are only talking about impact testing. We will discuss in detail when we get into fracture mechanics analysis. The notch toughness of low and medium strength BCC metals, as well as beryllium, zinc, and ceramic material, is strongly dependent on the temperature. This we know already. At low temperature, the fracture occurs by cleavage, while at high temperature, the fracture occurs by ductile rupture. Thus, there is a transition from notch brittle to notch tough behavior with increasing temperature. So we are kind of, accounted for why the, ductile to brittle transition is shown by some of the materials and how the other material behave under this high impact loading condition. That's all. In metals, this transition occurs at 0.1 to 0.2 of absolute melting temperature, Tm, while in ceramics, the transition occurs at about 0.5 to 0.7 Tm. So what is the significance of this transition temperature curve? The various definitions of transition temperatures obtained from an energy versus temperature curve or the fracture appearance versus temperature curve are illustrated in the figure. You see, since I said the test is quite simple, people have, adopted different terminology to identify the fracture behavior of materials. So let us look at this plot. It's quite interesting. This is the energy absorbed called CV versus temperature. And then you have this ductile to brittle transition S curve. But here you can see that there are so many divisions: T1, T2, T3, T4, T5. And then there are different regions demarked like, NDT, FTP, and so on. Okay. And then, so NDT, we are going to see all the nil ductility, temperature, fracture, what is that? Fracture appearance. Depending upon the fracture appearance, the temperatures are defined. We will see one by one. The most conservative criterion for transition temperature is to select T1 corresponding to the upper shelf in the fracture energy. So this is an upper shelf. So this is T1 we are talking about. So this is upper shelf and this is lower shelf. And the temperature above which the fracture is 100% fibrous, that is 0% cleavage. Okay. This transition temperature criterion is called fracture transition plastic, that is FTP. The FTP is the temperature at which the fracture changes from totally ductile to substantially brittle. So this is one very conservative criterion. Okay. Instead of looking at, in the middle, like we have generally shown in the BCC metals, but these are all different criterion for which, these temperatures are chosen. So the FTP falls in the upper shelf, okay, upper shelf of the curve. So below this, it is considered brittle, and above this, it is considered ductile. An arbitrary but less conservative criterion is to base the transition temperatures on 50% cleavage and 50% shear, that is T2. A better criterion. So this is a very conservative criterion. So T2 at least takes care of 50% cleavage and 50% shear. This is called fracture appearance transition temperature, called FATT. So this particular T2, wherever it goes, it is called FATD, fracture appearance transition temperature. Correlations between Charpy impact test and surface failures indicates that less than 70% cleavage fracture in Charpy bar indicates a high probability that failure will not occur at or above the temperature if the stress does not exceed above 1/2 of the yield stress. So this is all some thumb rules people keep to predict the material behavior. Okay. Roughly similar results are obtained by defining the transition temperature as the average of the upper and lower shelves value. This is T3. So it is almost like the middle of the S-curve. A common criterion is to define the transition temperature T4 on the basis of an arbitrary low value of energy absorbed, CV. This is often called ductility transition temperature. T4 is ductility transition temperature. And then another well-defined criterion to base the transition temperature on the temperature at which the fracture becomes 100% cleavage. This point is known as nil ductility temperature. So what is that? This is nil ductility temperature. The NDT is the temperature at which the fracture initiates with essentially no prior plastic deformation. Below the NDT, the probability of ductile fracture is negligible. Okay, just finally, what are the important metallurgical factors affecting this transition temperature? Very important. Changes in transition temperature of over 50 degree can be produced by changes in the chemical composition or microstructure of mild steel. This is just an example. So what is the message? By tweaking the chemical composition or by doing a proper alloy design or microstructure, that is proper heat treatment, you can have a control of transition temperature in the order of 50 degree. 50 degree magnitude you can control. Other than that, it is intrinsic. That's what it means. So this is a typical energy versus temperature plot. This is for the as a function of carbon, how this the dPdt curve changes. This is a very popular diagram which is given in most of the textbooks. The largest changes in the transition temperature result from changes in the amount of carbon and manganese. We are now talking about with respect to steel alone. We are not talking about any other material because this is very popular material and which has been used by many decades. Still steel is the workhorse material, right? So the 20 joule transition temperature for V-notch Charpy specimen, that is ductility transition, is raised about 14 degree for each increase of 0.1% carbon. So every 0.1% of carbon addition, then you see that there is a 14 degree difference. This transition temperature is lowered about 5 degree for each increase of 0.1% manganese. Increasing the carbon content also has a pronounced effect on the maximum energy and the shape of the energy transition temperature curve. So this is interesting, not just the values, the total shape of the curve itself is changed with the alloy chemistry, especially carbon and manganese, which is discussed here. The manganese is to carbon ratio should be at least 3:1 for satisfactory notch toughness. Maximum decrease of 50 degrees centigrade in transition temperature appears possible in going to higher manganese ratios. So this is one typical example where the chemical composition controls the transition temperature. So I think with this I will stop here, and I think we have covered most mechanical testing, which are very common, and then we will now move on to high temperature deformation. Thank you.